Saturday.
Weird.
Tuesday. I think I have Tuesday. No, wait.
Okay.
I got Monday.
Welcome to Thermodynamics. Oh, let's see now. Get my act together here. I handed back, or the back shelf has the air motor labs that I returned, and I wanted to go over just sort of look at some of the data from that, to highlight some things. I got the data for the various groups. What I should have split out separately, because there's a kind of interesting thing. And some of the errors people had was the amount of work the pump is putting into the water is from the suction side up to the power side. So it started off at 0 on one side, there was a negative. As you started pumping water, it had to suck. So the power went, or the pressure went down on that side. It may have actually been like 5 psi and it went down like 3 psi, it went down 2. Well, some people subtracted that from the high side. So it was 20 pounds here, and 2, it should have been 22. And if you did it, got the sign wrong, you'd say, oh, it only was making 18 psi pressure increase, but it was really, you have to add that suction. It's really the difference, P out minus P in, but P in was negative, and they got a double negative, it adds, reinforces. So that was a fairly common thing, but I'm going to pick one of these, maybe this one, and you'll see. The other thing, at a given RPM, if it was, and that's why this RPM matters, there's a certain volume of fluid that's pumped forward, and it's always the same volume being pumped forward by the gear teeth. But as the pressure comes up, more leaks past it, right? Higher pressure, you get more leakage. So at essentially 0 pressure, it turned out to be 4 psi, you get the highest volume flow rate. But as the pressure increases, it's still pumping the same amount of fluid forward, but it's the difference between this and this is how much fluid's going backwards. And that's why your efficiency down here, you had poor efficiency because all the friction in the system was eating up your power. And you got up to here, suddenly you had most of the fluid going forward, and it's actually doing some work, but you don't have so much leakage. So your highest efficiency is somewhere in here, and then it started tapering off because you're putting the work into putting the fluid forward, and it's squirting back around. You know, you had basically 2 gears meshing like that, but on the 2 faces, there's a seal there, but if you put too much pressure on it, then if the seal is too tight, then it gets hot and it wears out, and then it's not a seal anymore. If it's too loose, it's not a seal anyway. So it's that the seals and pumps, where the motion happens, that's usually the failure point. I ran a brewery for a while, and there was, there's always a place where the rotating seal and the stationary housing and the rotating shaft, there's something that has to rotate, and they'll have a spring that pushes something against something else with enough force so that there's more PSI on that surface than there is in the fluid, so the fluid doesn't lift it off and sneak through there, but there's always a little drip going on. In fact, you want a little bit of a drip going on because otherwise that seal gets really hot, high friction, and then it wears out. So you're going to have some of that. Some way that pumps fail is if you have, like, you know, in beer making, you got basically a sugary solution that you're pumping out of the brew kettle before it ferments. It's high sugar. Sugar gets sticky if it dries, and that stuff leaks through the seal. And then if you didn't also follow that, clean the pump immediately, run some water through it, have it pump some water so that some water leaks through. That stuff would dry, and then when you start up the pump, that seal wouldn't rotate, something else would rotate that wasn't supposed to rotate, and then your seal goes bad really fast. But I'm going to pick a couple of these, and you'll notice. So this 905 psi, gallons per minute. Hello. No, I just want you to open up. I'm gonna try there. I hate it. It's right there. It's in there. They won't let me look at what I put in there. Oh no, wait a minute. There it is. There we go. Okay, look at the 900. 0.78 psi at the highest flow rate, and if we go down to 1.85 gallons per whoops. That was at 2.1 gallons per minute. 1.85 is 0.59 psi. It's coming down. And 0.38. If we look at the next one, we were going 2.1 gallons per minute. Now here we're at 950 RPM. I bet you we're still going to see something close. Let's see, this one said it was 0.78. Well, actually, let me go down. The 1000 RPM group would have had the same data, same machine. They got a 0.94. They had less GPM because of more back pressure. Oh no, they have more GPM. More GPM, more gallons per minute, higher back pressure. Higher gallons per minute because they're going faster RPM. If you look at some of these that have some of the same values, there's a 0.78 at 2.1 gallons per minute. There's 0.84 at 2.2. So anyway, you see there's a trend for all that. I put in the data and cranked a bunch of numbers. And oops. It's something, might be my calculations, or it might be a data thing. I'm not sure what's going on here with the 900 RPM group. One can tell that's probably something different about either the calculation or the data, probably something messed up in my calcs. You can see there's a trend, there's a peak, and then it trails off. What's not easy to see is all of the 800, 900, 1,000, 1100, they're all in one unit, and the 850, 950, 1050, 1150 are on a different one. So you could actually see a difference between the two. There's a data point there that was not yet. Should be up there somewhere. I didn't check my didn't want power out versus power in. Now this is efficiency versus power out. If you do power out over power in, you should the slope of the line, the slope of this line should be reported if you do power out versus power in. Basically, it's the same information, except now the slope of the line says, the steeper slope says more efficiency, and the lesser slope means less efficiency. I don't know if that tells you as much as the other one does. This one is water volume per revolution versus pressure. Again, it's a constant volume pump. Every time it rotates one revolution, it carries fluid around. And it should be the same amount of fluid because the teeth aren't changing size. And they're closely monitored. And so if there was no leakage, but you had at really low back pressures, it should be constant. The faster you go, the more you pump. And you do. You pump more as you go faster. But if you divide the RPMs into the GPMs and gallons per revolution and turn in cubic inches, you get this chart. You can see they're all fairly consistent. But now we could look and see, is there a difference between the 800 and 900 and the 1,000? 800, 900, well, 1,000. Maybe they're on a different one. and the 850 and 950. 850, 950. So these two curves are a little bit lower than these two curves. And they're kind of matching, which tells me that maybe, but this piece of data sort of questions that. But tells me that the unit that was on the 800s and the 900s probably has more leakage inside, probably needs the seals changed sooner than the other unit that was 850, 950. They're the identical thing, but one's got more seal leakage. And then I just, what was the leakage in each? Same information, but now it's kind of like, okay, just how much leakage per revolution is there? The leakage is going up with pressure. Different way of looking at the same thing. Power loss versus pumping pressure.
So we have 0 power loss?
Yeah, that's got to be that's a data issue. I didn't check these ones. I used some information from last year, or format from last year, and I didn't check to see what that one is. Yeah, it's no one had that. So you can tell you can't trust that one because it goes way up and down. Probably this was a data point that had a 0 in it, but interesting thing is they're all coming down to one point here. They're coming down to a power loss of, it looks like it takes close to 15 to 20 watts just to turn your pump. And you can turn that into a torque and say, this is how much torque it takes on average. You know, and if this data was tighter, it would all come down to one point. You could say, well, without measuring the torque, I can measure the input and output and come up with I'm losing this much power because of my inefficiency. When you come down to the point where there's no back pressure and essentially no leakage, this is basically the leak flow rate thing. You can come down to a point where you say, I'm losing that much power, and it's not because of leakage. It must be because of just the friction of air motor, whatever couplings, misalignments, and internal friction, all that stuff bundled together. And it just takes that much power to turn the pump system. And same way, here's friction torque. If I take that power loss number and just decide it's all friction power, they're all coming down to, here's how much torque. And these are coming kind of into really close. At 0 pressure, at the low pressure, it's all coming down to 0.2 Newton meters worth of torque. Would explain the power losses that we're having. And this is an outlier for whatever reason, but that they're kind of coming together quite nicely. And efficiency versus RPM, that doesn't tell us anything. Anyway, there's a whole lot of stuff you can get out of that data if you could take data and come up with, you know, how much torque do you need to turn this thing when it's not working? How much so, does that make any sense? So, all this stuff follows from a little bit of data. You bundle it together, and you know, there's more. You know, some of this stuff. So we have a certain amount of power in, and you've got power out. If you subtract from power out, oops, come on. I had, if I have this much leakage, then I could say the leakage amounted to this much power. If I subtract the leak power, if I take the power in, subtract from it, power out, you have the power that was lost. In and out, right? You lost some. Where did it go? Some of it went to the leakage. We know that it was pumping forward and then it's leaking backward. So that much power was due to leakage, and if you subtract the leakage power from the power lost, then you had friction power, and then if you take that friction power, then you can mess with, so there's friction power and there's the internal leakage power loss. So that's where all that stuff came from. So yeah, there's inefficiency. Where is the inefficiency? So the question is, should you change the seals on the pumps? Should you, grease the motor? How do you improve your efficiency? That doing a study like this could get you that kind of information. So that's what I had to say about that. Those of us who took an early vacation, this first part of this, the chapter 24 is not in your book, it's online in the Canvas site. It's all about heating, ventilating, air conditioning kind of things and the loads involved with that. And just as a sort of a quick rehash, thing that really matters is in the ideal gas law. The gas law, ideal gas law, is based on number of molecules, not the mass. So let me use my illustration here. If you have a 1 cubic meter box, its atmospheric pressure, 100 kilopascals, and it has a mixture of nitrogen and oxygen and methane in this case, in the example. And they gave us how many kilograms of each there were. This is, okay. There's this many kilograms of oxygen and 32 grams per mole of oxygen. The question is, how many moles of oxygen are there? And if you do the math, 3 kilograms divided by 32 grams gets you 93, almost 94 moles. A mole, 6 times 10 to the 23rd, it's a bucket full. And you do that for nitrogen, you find it's 178 moles. If you do that for the methane, you find that it has 750 moles. And if you add all these up, you see how many molecules there are floating around in space. And then if you do a proportion of that, so this one ended up being like 9.2% of the total. It had 93.75 out of 1,022 moles. 9.2%. This one's 17%. Mass-wise, this is 15%. So it actually, because it's the heavier molecule, it has less percentage of number of molecules, but it's a larger percent of mass. So you got to watch that. But it turns out the ideal gas law is talking about this column. And if we took this mixture of stuff, and now we took at atmospheric pressure, put it into a 1 cubic meter box, which is about what the white tank in the back of the room is. It's about a cubic meter. And we had a little divider, and we put a hole in the middle of the divider. And first, it's up against the wall here, and I start grabbing all the nitrogen molecules and start throwing them through the hole. And every time nitrogen comes by, I throw it through the hole and fill up that divider. It starts to move away from the wall. And when it's all filled up, all the nitrogen's been put behind that wall, it would take up 0.175 cubic meters. 1 total cubic meter. If I then sealed that and got another magic divider with the hole in it and started taking all the oxygen, started throwing them through the hole, grab them when they came by and put them through the hole, you know, it would take up 9.2% of the space. And the rest of the space would be taken up by the rest of the molecule. Now they're all separate. And now I do like the magician, and I cut these and have these slices, and if they were all at 100 kilopascals at these volumes, ideal gas law says PV equals nRT, and if N is the same and the R is the same and the T is the same, that's a constant. So P times V, well, if I take this one here that was 73% of the total volume, that's 100 kilopascals. And now I take it and expand it out to 1 cubic meter. It was 73% of a cubic meter at 100 psi. Now I accordionize it, and now it's 1 cubic meter. What's going to happen to the pressure? It's going to drop. How much does it drop? Well, 100 times 0.73 is the same as 73 times 1, right? So if I pull it out to 1, now the pressure is going to go down to 73 kilopascals. And likewise, if I do that for these other ones, the nitrogen, pull it out, it was 17% at 100 kilopascals. Now I go out, now it's going to be at 17 kilopascals if it's in 1 cubic meter. And if I take this one, it was 9%, and it was sliced and expanded out, it's going to be 9 kilopascals. And that's the way gases act. That's the way the moisture in the air acts. The partial pressure is proportional to the number of moles in the air. You know, whatever. We have oxygen and nitrogen. Nitrogen in the air was about 79% of the total. Oxygen's about 21%. So and we don't really care about the nitrogen. We breathe in the nitrogen, use the oxygen, breathe out the nitrogen plus CO2 that we've converted, right? The actual pressure of oxygen that's causing, stuff happening in your lungs is 21% of atmospheric pressure. So it's really not 100 kilopascals, it's 21 kilopascals. If you go to the top of Mount Everest, atmospheric pressure is about 1/3 of what it is. Atmospheric pressure is like 33, but now the oxygen pressure, which was 21, now it's going to go down like 7 kilopascals. There's some pressure at which it doesn't do the exchange. You have to have a certain amount of pressure for the oxygen pressure to push itself into your bloodstream and out. So the blood saturation drops with elevation, and that's why, like you go jogging at 10,000 feet, you will know it. Anyone go jog at 10,000 feet? Did you know it?
Headache, I got a lot of headache and stuff.
Yeah.
Chewing coca leaves though.
Well, that's probably dilating things or whatever. So that's kind of the whole, that's the important thing. So there's this, it turns out if you do the same thing, you can do it for volumes and you can do it for pressures. I did first the additive volume thing, partial volumes. When I stuck it behind the wall, that was a partial volume. You could say it took up that much volume out of the total, or you could say it takes up this much pressure. You get your choice. You can do it one way or the other, but you don't do them both at the same time. Mostly this partial pressure concept is what we're going to use, though. It explains why clouds do what they do, things like that. So that's where we were yesterday. And the total barometric pressure that we deal with is the pressure of the oxygen and nitrogen and all the other stuff in the air, plus the pressure of water vapor. Water vapor is going to be the next biggest thing. So we're measuring, there's a total pressure, which is all the stuff together, and then it turns out the vapor pressure of water becomes the largest load in heating, ventilating, air conditioning, especially if there's condensation going on. So saturated air means that the pressure of the water vapor in the air, enough molecules of water have come in such that the partial pressure of the water vapor equals the saturation pressure from our saturation tables. And that's straight off the steam table. If the partial pressure gets that high, that's 100% relative humidity. Now, what's that feel like? If on a hot day in some place that's got high humidity, a tropical forest, I experienced it in Atlanta, Georgia in the summer. It's just, you feel sticky. Why do you feel sticky? Because there's so much moisture in the air that there's no real incentive for your moisture to evaporate into it, and it's evaporative cooling is why you sweat. And if you sweat, you're trying to cool off, but your clothes get sticky because that's high humidity, and that's that saturation thing. So basically, we're going to just teach. We're not going to worry about what's in the air, all the the xenon and the helium and whatever else is in there. It's all pretty ignorable. It's out there, but we're not going to worry about it. In fact, it's oxygen and nitrogen. The total barometric pressure matters. It'll vary, but that saturation pressure of water, that saturation really doesn't. It's the water pressure is all about whatever water saturation at a given temperature is. Yeah, it can be half the energy load, especially for air conditioning, can be due to condensing moisture out of the air. So there's a thing they call relative humidity. And the thing they call relative humidity, oh boy, I don't know why this does it to me, but it does. Relative humidity is what's the pressure of the water vapor relative what is the saturation pressure at that temperature. So that's usually what they tell you. At the back of the room, there's a thing on the wall above the microwave. It tells you what temperature is and the relative humidity inside and outside. And that's the pressure ratio. And it turns out it's a mass ratio, and we'll get into this one. That's all buggered up, so I'm not going to spend a lot of time explaining that. But there's also something called, so remember, relative humidity is about a pressure ratio, and specific humidity, also called humidity ratio, that is a mass ratio. How much water vapor is there per kilogram of air? And this is actually fairly easy to explain. The difference between the total pressure and the pressure of the water vapor would be pressure of the air. And the pressure of the water vapor up here, well, it turns out pressure times volume, PV equals nRT, and anyway, these pressures are stand-in for the number of molecules. And so this is, if you did this in terms of trying to find the mass of the air, the mass of the water would be a volume times the density. From ideal gas law, you can get density from the formula. So this is like the number of molecules, this is simply the ratio of how much does water vapor weigh? H2O, two H's plus O is 16. 16 plus, yeah, plus 2. Weighs 18. Air is oxygen, nitrogen, they say at about 29. If you take 18 and divide it by 29, then you get this. So the pressures are standing for the ratio of the number of molecules, and this is molecular weights. So this, you can measure pressures and come up with masses. And you can measure barometric pressure, and then if you know your relative humidity, ratio of pressure to saturation pressure, and you know the temperature, then you can come up with what this volume is, and there's ways to figure that out. So that's where this comes from, and specific humidity is actually tells you how much water vapor you have by mass. There's a bunch of different temperatures. So up till now, we've only been talking about room temperature. That's what's called dry bulb temperature, because there's also wet bulbs and there's isenthalpic temperature. Okay. Wet bulb and dew point and whatnot. Anyway, dew point temperature is if you take the air that you're dealing with and you chill it down to the point where the water starts to condense, and that's dew point. They call it dew point. Why is that? Because grass collects dew. It gets cold enough. If you put something out in a room and you chill it down to the temperature where moisture starts to collect on it, it will actually harvest moisture out of the air. That's the dew point temperature. So it's for a given amount of moisture in the air, you chill it down until it gets to its saturation temperature for the actual pressure of water vapor in the air, the partial pressure. That's dew point. It's the saturation temperature at whatever water vapor pressure you have. And then there's wet bulb temperature. If you take a wet washcloth and swing it in the air, it's going to go to an ultimately low temperature. Now you're taking the energy in the air and you're trying to force it to 100% relative humidity. In one case, you're taking the water vapor, you're chilling it down until it becomes saturated. That's one temperature. This other one, you're using the energy in the air. With that same amount of energy, what if it was forced to saturation? You take the energy in the air to vaporize. That's what the wet bulb does. The wet right around it is 100% relative humidity, but it's using the energy in the air. You're not adding energy or taking. You're not chilling the air to do it. You're just using the energy in the air. It's going to vaporize some, and it's an intermediate point. It's not. It's colder than whatever your temperature your dry bulb temperature is. It's colder than that, but it's not as cold as the dew point. So again, my dad used to, when I had a fever, he'd take a wet washcloth and swing it in the air and then put it on my forehead. You can predict that temperature. Yeah. They all go about adiabatic saturation. Adiabatic, what's that mean? You're not adding energy, you're taking it away. It just uses energy and converts. Lower temperature, higher humidity. It takes energy to force the vapor up. And from the ideal gas law, we can come up with a volume for dry air of, again, take the total pressure, subtract the water vapor. That's the pressure, absolute pressure of the air itself. And you get times the R value for dry air and the temperature. These all have to be absolute values. That's going to give you a volume per kilogram of air. It changes with temperature, it changes with pressure. For the most part, the pressure is not going to change a lot. This is going to be, it changes with altitude for sure. But most of the time you're talking about whatever atmospheric pressure you have. And the water vapor will actually reduce this a little bit, depending on vapor pressure, what you're dealing with. The total enthalpy of the energy in the air is related to its temperature. But if you think about dry air, the plain old air, you've got a C sub P times a change in enthalpy. This should all be changes. Delta H equals C sub P delta T. And this is a number like 1. For the water vapor, there's a C sub P times a delta T plus HFG. This number might be the point, like, I don't know, 1 or 4 kilojoules per kilogram. This number is like 2,000. That's why it's the 800-pound gorilla. Or maybe it's 1,000, 2,000 kilojoules per kilogram, I think. 1,000 or 900-ish BTUs per pound. If you start cooling down and you get to that saturation point, and now you're having to pull moisture out of the air, it's going to resist it because of this term. You have to condense the moisture. And that's where the load, especially for air conditioning, comes in as like an absurd load. It's the latent heat, phase change. So this term, how much time of mass of water vapor, so you can, that's why we can use this mass ratio. That's the mass of water vapor relative to the mass of the air. And you can just multiply this for the air and use that mass ratio in that calculation. Here's some of the numbers. Yeah, 1.82 for water vapor versus 1 for just the air. 2,500 for the phase change on the vapor if you have to condense it, which usually happens in air conditioning. So you could do all this stuff, and it sounds like you do a whole lot of calculations, and this is really gross, right? Interpolations, yeah, so much fun. But let's look at an example. For instance, a room 5 meters by 5 meters by 3 meters. How big would that be? 5, like 15 feet by 15 feet by 9 feet. I should make it as big as this room, whatever it is. Atmospheric pressure is 100 kilopascals, 75% relative humidity. How much water vapor is dissolved in this air? Let's see. At 25 degrees C, what this tells me, whatever the pressure, I don't really care about that so much at this point. It doesn't really matter. I want to know about the water. We know at 25 degrees C, if it was 100% relative humidity, we know we can look up what that pressure would be. And it's only 75% of that pressure. So pressure, the actual pressure of the water vapor, if that's true, would be 75% of the saturation pressure. Oops, too high. So according to this, what do we have for a saturation pressure? Oops, I'll find that's the pressure table, what temperature table? What we know is 25 degrees C. So if water vapor was all the way up to 3.1698 kilopascals, which would be 3% of the total, then it would be 100% relative humidity. But it's only 75% relative humidity. So where were we? 1698 pascals. So what does that give us? Something like 22.4-ish.
3.377.
Okay, for our next trick, what's the mass? The mass is going to be the density times the volume. And what's the density? It should be pressure water vapor times R for the water vapor, which includes the molecular weight, and temperature absolute. So that's all that term times volume, and the R, I just looking up here, the gas constant for steam is 0.4615 kilojoules per kilogram Kelvin. I'm going to pull my trick and say that's 0.4615 kilopascals meter cubed per kilogram Kelvin. So pressure water vapor is 2.377 kilopascals. Divide that by 0.4615 kilopascal meters cubed kilogram Kelvin times 298 Kelvin. That's going to give me kilogram per meter cubed times 5 times 5 times 3, sounds like 75 meters cubed. We've got the density of the water vapor in the air at its partial pressure, and its partial pressure is this much times the volume in the room. So that should get us what? Meters cubed, we're going to cancel, end up with kilograms.
We are 1.296.
So you could have, and that's, about a kilogram to a liter. So that room, 15 by 15 by 9 feet each, 5 by 5 by 3 meters. Could have like 1.3 liters of water. If you chilled it down enough, you can harvest that much water just out of the air. Now it turns out there's other ways to do it, and we'll talk about that. We're going to actually, the next couple days is Joy of Joys. We're going to have quizzes, not tomorrow, but probably the next day and the next day, and in lab. But we're going to be related to the final, and one of them is, you don't have to necessarily do this calculation. We will do this this all over again. But all of that is built into this chart. This chart is your friend. You go to 25 degrees C, you go up to 75% relative humidity, and you come over here and it says it's 15 grams per kilogram of dry air. You know how much air we have, then that's a proportion. So, there you have it.